Hey everyone, in today's video, we're going to be solving the problem insert into a binary search tree. So the question says you're given the root node of a binary search tree and a value to insert into the tree. Return the root node of the BST after the insertion. It is guaranteed that the new value does not exist in the original BST. Now, notice that there may exist multiple valid ways for insertion. As long as the tree remains a BST after insertion, you can return any of them. Okay. So what the question says is that we're given a binary search tree, maybe something like this, and we're also given a value, which is 5 over here, and we need to insert that value into the binary search tree in such a way that the whole definition of the binary search tree, where the left side is lesser than the root node, which is lesser than the right side, is maintained, right? So basically, this is what the binary search tree algorithm basically stands for, that everything on the left is smaller than everything which is of the root on the root hand, which is on the root. Basically, if 4 is our root, everything to the left of 4 is smaller than 4, and everything to the right of 4 is greater than 4. Okay, and each individual subtree of the binary search tree should also be a BST, right? So over here, if we go to the left, we have 2, and everything on the left of 2 is less than 2, and everything on the right of 2 is greater than 2, right? So that property of it should also be maintained. Okay. Now, when we have a value like 5, when we enter it into it, there are multiple ways of making this tree into a binary search tree. One possible way, as you can see, over here, is that you can have 4 over here, right? What can happen? Now, 5 is greater than 4. So we move to the right hand side, which is 7. Now, 5 is less than 7. We can go to the left. And when we hit a point where there's nothing present, we can just, add 5 to that side. Right. So this is one way you can make this into binary search tree. Now there can be a different binary search tree where we just make phi the root node. We try to find the value of 4 from it. Like if 5 is becoming our parent node, the very the main node, which is the head node over here. We can just then we need to find a appropriate place for 4 in this case. One appropriate way, you can just have 5 over here, then you can just take 4 and start looping 4 from the left hand side, because 4 is less than 5. You can start looping. You can see that 2 is less than 4, so we go to the right. 3 is less than 4, we go to the left. You can again go to the right, and then since we have nothing present, we just add 4 to the right hand side, right? So there are multiple ways of making this tree into a binary search tree. One more possible way could be you have 4 over here, you add 5 in place of 7, and you add 7 to the right of 5 in this place. So that this also again would become a binary search tree. Right. So there are multiple ways of making a binary search tree. And without complicating it much, the very easiest way is just to, traverse the node we are given and find an appropriate place for it. For example, over here, we've just found an appropriate place for phi rather than making too many changes on the current tree itself. Right. That's the most easiest way, and we're going to do it like that only. So, firstly, let me just show you what the code is like. Right. So, this is what the code is. Firstly, what we're going to do is first thing first, we're going to check if the tree is empty or not. If it is empty, we're just going to return the tree node as our output of the answer, which is going to be tree node of val, which is 5. That is going to be the output. So we'll only have one node with the value of 5 in it, which is going to be the output in this case. Right. This is only if the tree is empty. All right. Now, when the tree is not empty, what we're going to do is firstly, we'll keep a head equal to root, because we want to return in the end the main root of the tree. Because we're going to be traversing through the root node, we'll be in the end, we'll be at the very last index where we insert this 5 over here. We'll be at that point. So we don't want that when we return the root, when we return the answer. We want the very root of the node to be returned. That's why we'll just keep a value head over here, which we return in the very end. We won't do any changes to head over here. If all the changes is going to happen to root over here. All right. Now L is equal to none. Why are we keeping L is equal to none? Let's see that when we go forward. Firstly, we'll loop through the tree until unless we hit a point where we reach the very none point of it. For example, when we reach 7 and we see that 7 we have to go to the left of the tree, check whether there is a value present, because 5 is less than 7. But over here it'll be a null value, so we just insert 7 over 5 over here, right? So we're going to loop until we hit a point where it's going to be a null pointer for us. Right now, what is this L going to do for us? This L is just going to signify whether we insert the node to the left of the current tree, current node, which is 7, or to the right of it. So over here, what we're doing is we're keeping, again, a variable cur, which is equal to root, which is going to be basically keeping a check of this point, of this 7 over here. Firstly, okay, so let's just do a trial and understand. Firstly, what we're doing is we're checking if the current root dot val, which is 4, is less than val or not. So we're checking over here if our 4 is less than 5, right? So 5 is great. Obviously, it is true because 5 is greater than 4. Then what we'll do is we'll make cur equal to root. So our 4 will be equal to cur right now, and our root will be equal to root dot right, which is 7, right? And we'll make this L equal to false because if there was no 7 present over here, then we would have just added this 5 to the right of 4, to the right of cur. Okay, so this is what's going to happen. Right now, again, since we go to the right, we're going to check again. When we check again, we see that, we'll check with 7 this time. Is 7, which is are going to be root dot val, is less than 5 or not? So it's not. So we go over here and we check for this value now. Again, when we check over here, we'll make this curve equal to 7. Right. Initially it was 4, but now it's going to be 7. It'll be keeping the pointer. This will point to the very head node. This will point to the current head node. Okay. So for now, our current head node is going to be 7 because we just moved from 4 to 7, and we'll just go to the right of this tree where we go over here. Now, when we go to the right of the tree, we'll also make this true, left of the tree, sorry, and we'll make this L equal to true. What this L is going to do is we'll just check if L is true now. What this L is going to do is will just help us understand whether we need to insert the node to the left of the current node, which is 7, or to the right of it. Right. Since we went to left from 7, we understand that when we went over there, there's nothing present. There's no left, no right. We just have two null pointers for 7. Since we have only two null pointers, what we're going to do is we're just going to check where this L is just going to signify where do we have to insert that node, whether we have to insert it to the left of the current node 7 or to the right of it. And when since L is true over here it's becoming true, we just add it to the left of the tree node, which is we just add cur dot left equal to tree node dot val, which is 7 pointing to 5 over here, and in the end we just return head. Okay, so this is how you solve the problem, guys. And let's just run the code. Yeah, it's running, and let's submit it. Yeah, it's submitted, guys. All right, guys, that's all for today's video. If you like the video, do like, share, and subscribe. Do let me know in the comments if you have any more suggestions for videos you'd want to watch next on the channel. Do check out my podcast as well. And until next time, guys, thanks for watching.